So this part of the course, we're going through different techniques for finding antiderivatives. Okay, so it's going to feel a lot different than the first week. We don't want to lose sight of all that stuff in the first week is very important, but this stuff we have to kind of go through these different techniques. So the next technique we're going to have is, so we've done undoing the chain rule. We said that's always our first thing we look for. It's the most common thing that shows up in these harder antiderivatives is undoing the chain rule. So we always look for that first. Then we might, if it follows kind of the pattern that we saw on Friday, then we would look for undoing the product rule, okay? The next thing is, these are pretty easy to spot because we're going to talk about finding antiderivatives of a rational function. A rational function is a fraction of two polynomials. A fraction of two polynomials. Okay, so the first thing you look for is if the degree of the numerator is greater than or equal to the degree of the denominator, you're going to begin by long dividing the fraction. And I think one of your web work problems, as you're working along, if you're on the right track, you're going to get this very thing. Okay, so here's an example. Integral of 2x squared over x plus 1. So this is what we call a rational function. It's a fraction of two polynomials. And the first thing you look for is if the degree of the numerator is greater than or equal to the degree of the denominator, like this one, and like one that will come about in your homework, okay? If you're on the right track in your homework, you'll have a case like this, where the degree of the numerator is greater than or equal to the denominator. So you're gonna long divide. So if you remember from Algebra 2, long division, we're doing x plus 1 into 2x squared, and that's the same as 2x squared plus 0x plus 0. And long division of polynomials is very much similar to long division of just numbers. So we're saying we've got x, we want 2x squared. So what do we need to multiply x by to get 2x squared so that it'll go away when we subtract? We need 2x. So we need 2x. So we're going to put a 2x up here. So we're going to multiply down. It's long division. 2x times x plus 1 is 2x squared plus 2x. Then we subtract, and that's 0. That's what we wanted. And we got 0x minus 2x, which is minus 2x. And we're going to bring down 0. And now we're saying, what do we need to multiply x by to get minus 2x? Minus 2. So we get minus 2x minus 2. We subtract. That's 0. That's what we wanted. This is plus 2. Nothing else to bring down. So this is our remainder, right? So this fraction 2x squared over x plus 1 is the same as 2x minus 2 plus 2 over x plus 1. Can you give me some toilet paper from the bathroom? So when you do the long division, you get this, which is very, very easy at this point for us, right? Easy antiderivative, 2x, x squared, minus 2x, plus antiderivative of 2 over x plus 1. We're going to use 2 what? Please know this. You're all thinking it, right? Thank you. Natural log. I need absolute value. Plus c. Right? Antiderivative of 1 over something, natural log. Because the derivative of natural log is 1 over, or to the negative 1. Now, sometimes the long division is all you need to get an attainable. That's a new rational function. That has an attainable antiderivative. We don't have to do it long divided. We just know that that's 2 natural log. But sometimes, thanks. So sometimes we still have to do more on this. Okay, so we'll get this remainder quotient here, this remainder fraction, and we'll need a technique possibly called partial fractions. Which is the main topic of today. Okay, so sometimes just the long division does the trick, and we're done. We got it. But then this remaining fraction here, it may be that n. So we're going to get n less than d in that, and if we can't just apply natural log, then we need this technique that we're about to learn called partial fractions. But in this example, we didn't need that. I just wanted to show you long division. But the main topic today is this technique called partial fractions, and that's what you use if the degree of the numerator is less than the degree of the denominator. So let's see that. Okay, questions on this first example? Like I said, there's a problem where you're gonna need that to finish the problem that you had in Friday's, the web work assigned Friday, due Wednesday. Okay, so the next thing is so I should have said if n is less than d, and I can just type that in. Why don't I just type that in? All right, so now here's the next thing. If the degree of the numerator is less than the degree of the denominator, and d can be written as a product of factors, then we're going to decompose the fraction into the sum of partial fractions. And let's see an example of this. And this is what we're working on today. So here we have an example. 5x plus 1. 2x squared minus x minus 1. And let's say we're going to do that from 4 to 20. And now, before we do this example, I just want to review. I want you to tell the person next to you what's the meaning of that big expression. What does that expression mean? Do we remember from week 1? Do you remember from week 1? What's the meaning of that expression? Tell the person next to you. Go. Okay, volunteer to tell us what that means. Somebody new, somebody who's not spoken out before. So to me, this little question I'm asking you right here is as important as the next 10 or 15 minutes we're going to spend doing this problem algebraically. To me, this is probably more important that you can interpret what those symbols are telling. Yes, in the back, tell me. Good. He says the amount of accumulation or the amount of change, right, of some quantity or an amount of accumulation when x goes from 4 to 20, when the rate function is 5x plus 1 over 2x squared minus x minus 1. So hopefully that's what you said to the person next to you. If not, learn that quick, okay? Because that's what this is all about. That we've got a rate of change function, and we're going to sum up the total amount of change from x equals 4 to x equals 20, and that's what this will give us, okay? So how do we do this? What we want to do is, first of all, long division is off the table. Degree of the numerator is less than the degree of the denominator. So we're going to see if this denominator can be factored, then we can use this partial fractions technique. So I'm just going to take off the limits for now, so they don't. So we know that once we get the antiderivative, we know how to evaluate it from 4 to 20. That's easy. So we'll just not let that distract us. So can the denominator be factored? And the answer is yes, it can. We just got to figure out how. And if it can, then we can use this partial fractions approach. So 2x and x, and then we got -1. So multiply to -1, add to -1, because we got -1x. So should that be plus or minus here? Be +1 here, -1 here. You all should know how to do that. Factor a quadratic. Okay, so what we want to do is continue to rewrite this, but we want to rewrite this as, so when you add fractions together, you get a common denominator to do it, right? So it's kind of like we're going in reverse. So it's like this was our common denominator that was the result of adding fractions. So what were the original two denominators? So when you're adding fractions, how do you find the common denominator, right? If they have no common factors, you just multiply them to get the common denominator. So the original denominators would have been just those factors, right? 2x plus 1, x minus 1. So it's like going backwards from adding fractions. We're decomposing this one fraction into its original sum of fractions. So you're used to adding fractions by finding the common denominator and making one big fraction. Decomposition means going the other way. Okay, so then the question is, what numbers up here do we need so that when we add those together, our new numerator becomes 5x plus 1? So we need to figure out what a and b are. So that if we were to add these two fractions together, we would have the numerator 5x plus 1. So what do? We're just gonna proceed on this thing on the right here. We're gonna add them together, keeping the capital A and capital B. So how do we add those together? What do we do? So we need our common denominator, which is 2x plus 1 times x minus 1. So what do we do to the first fraction to get ready to add it to the second? We need the x minus 1 in the denominator, so we need the x minus 1 up here. Okay, and then what am I going to do to the second one? Multiply top and bottom by 2x plus 1. So now I've stepped outside of the integral now. So this is kind of the premise of the problem right here, that we need to figure out what a and b is to rewrite the integral to be able to solve it. But now, so now I'm just pulling that rate function out, and we're just going to work on the rate function now, and then we'll go back to our integral. So now what am I doing? I'm adding these fractions. I'm adding these fractions, so I'm getting my common denominator. And so I need to adjust the numerators accordingly. And so then I get a times x minus 1 plus b times 2x plus 1 all over the common denominator, which we already know is that 2x plus 1 times x minus 1. And so what does this have to equal? So this numerator has to equal what? 5x plus 1. So we're figuring out what are a and b so that that numerator is 5x plus 1. What's the capital A and the capital B so that that numerator is the 5x plus 1, and that will be the a and b that we need. Okay, so this numerator now is ax minus a plus 2bx plus b. And we said that has to equal 5x plus 1. So I'm just looking at the numerator. Because all we care about is the capital A and B. So if we can get the capital A and B, we can do the antiderivative. So that's what we're focusing on now. So basically, what's the coefficient of x? 5. So we're going to look at ax and 2bx are our 5x term. Did I make a mistake? Okay. And then the minus a and the plus b has to equal the plus 1 term. So the coefficient of x is basically a plus 2b. So a plus 2b, do you see that? A plus 2b has to be 5. And negative a plus b has to be positive 1. Did you follow it? Does it make sense? So I'm starting with what I know the form of my answer is going to look like, and I'm just going to add those together, add those fractions together, keeping my capital A and capital B, until I know that the resulting numerator has to be 5x plus 1. And if it is, that means that a plus 2b has to be my coefficient of x, 5. And minus a plus b has to be my constant term, plus 1. So now we've got to solve these. We've got 2 equations, 2 variables, and actually this one is very nice and friendly because I can just add these 2 together and the a goes away, right? A plus minus a is 0. So if I just add equations here, I get 3b equals 6. And so b equals 2, and use either equation to backtrack and find that a equals 1. When you get these system of equations, however, whatever method you want to solve the system of equations. Some people like using matrices. Some people like using substitution or elimination. So any technique that you've learned to solve that little system is fine. So now we got a is 1 and b is 2. Well, then that gives us this equivalent integral to the original integral we have. So this original integral then is equal to a is 1 over 2x plus 1. Let's try that again. Okay, so then that original integral is equal to 1 over 2x plus 1 plus 2 over x minus 1. And we're home free. Really easy now, right? So antiderivative of 1 over 2x plus 1. Natural log of 2x plus 1. But we know by undoing the chain rule, we're going to need 1/2, right? Plus 2 times natural log of x minus 1. and then either plus c if it's indefinite, or that whole thing from 4 to 20 like I originally had. Okay, questions on this first pretty easy example of, this is what's called partial fractions technique. Anybody have a question? I'm going to erase. Last chance. Okay. Here's another one. Okay, is the degree of the numerator less than the degree of the denominator? What is the degree of the denominator? It's the highest power of x for that polynomial, right? What's the degree? 3, right? You should be thinking 3. Because if you were to multiply that out, you'd have x times x squared, which would be x cubed. That would be your highest power of x. So the degree of the numerator is less than the degree of the denominator. Okay? So, and we've got a product of factors. So this qualifies for our partial fractions technique. So each of those factors is linear. So we have to come up with all the possible denominators we could have here. So we could have x minus 3. So we'll do A, okay? And then we could have x minus 2. But what have we not considered yet? Yeah, so x minus 2 squared. So then you say, well, should we have a fraction that has x minus 3 times x minus 2? No, because that would be redundant of these two added together, right? So you wouldn't have another one of, like this, x minus 3 times x minus 2. Why? Because that would be redundant. We've already taken care of that by the sum of these two. The sum of these two would have that denominator. So we don't need that. This is all we need. Now, one thing I didn't say last time was these numerators always need to be 1 degree less than the denominator of that partial fraction. Okay? So what about this one? Well, it's still, so what you look at is you don't look at the fact that this is x squared, but it's really still the factor x minus 2, which is degree 1. So all these are degree 1. It's degree 1. So is this. It's a degree 1 factor, but it's just squared. Okay? It's still a degree 1 binomial. So your numerator is always 1 degree less than your denominator. So we'll see an example next time where it's going to be something other than just a constant. But 1 degree less than degree 1 is degree 0. So that's why we're just using A, B, and C. We're just using A, B, and C because all of these denominators are degree 1, and your numerator, the general numerator that you're using, these capital letters A, B, and C, will always be 1 degree less than the denominator. Let's write that down. But this x minus 2 squared is still considered degree 1. It's still considered degree 1 because it's really just the factor x minus 2. It's just the factor x minus 2, but it's squared. It's two of them. It's x minus 2 and x minus 2. So it's still, we still consider that degree 1. Okay? Question?
Can you explain how you got the denominator for C? Why is it x minus 2?
Because we need all, so we got to take into account all possible factors, thinking about that we're adding together a bunch of fractions to get that fraction. Okay? So we're adding a bunch of fractions to get that fraction. So it's like, what are all possible denominators that we could have that are kind of exclusive from one another that could sum up to that fraction? So if we just did the first two, what would our common denominator be? It would be x minus 3 times x minus 2, not x minus 3 times x minus 2 squared. So another possible factor of this denominator is x minus 2 squared. We have to include that as a potential fraction that's added into these to get that. Did that help? There was a question on this side? No? In the back? Because x minus 2 is a factor of this, so there could be some constant over x minus 2 that you wouldn't be including. So it's like, what are all possible fractions that you could have that when you added them together, you got that common denominator, x minus 3 times x minus 2 squared. So it's possible that you have, since x minus 2 is a factor of that. There was another question in front? Okay. Is this... It's kind of hard to explain. So if you've got a better, some input, I would... All right, so let's go for it. Here we go. So what are we going to do? Now we're going to add these together. So we've got all this dx. So what do we need to multiply top and bottom of this one by to get the common denominator? X minus 2 squared, right? So I'm just going to go straight to that. It's going to be, the numerator is going to be a times x minus 2 squared. What do I need to multiply top and bottom by this one by? Just x minus 3? And another x minus 2, right? What do I need to multiply top and bottom of this one by to get the common denominator? X minus 3. So that's what the numerator would look like if I added those fractions. So let's note that. This is the numerator. We know what the denominator is. It's going to be this. Okay? And so here we go. Algebra time. So it's going to be ax squared minus 4ax plus 4a plus bx squared minus 5bx, check my math, plus 6b plus 6x, so cx minus 3c. Check my math. I think it's right. I think it's right. And we're multiplying everything out. And so then what? We're going to get, so now look, we've got what? X squared plus 1. So all the x squared terms together, their coefficients, are going to equal, and so this whole thing has to equal x squared plus 1. Or 1 x squared plus 1. So what equals the coefficient of x squared? A, we got an A, so I'll do blue boxes here. Ax squared. Those are our x squared terms. And I should say 1x squared, what, plus 0x plus 1. I really want to make this clear. So I need that whole numerator to equal my original numerator. 1x squared plus 0x plus 1. That's what I was originally given. Okay, then we'll do red next for the 0 terms. So negative 4ax, negative 5bx, plus cx has to equal 0x. And then finally, constant term, 4a, 6b, minus 3c, plus 1. So we're going to have 3 equations, 3 variables. We need a, b, and c. So our x squared, so it's going to be a plus b equals to what? Coefficient of x squared. Negative 4a minus 5b plus c equal to 0. 4a plus 6b minus 3c equals 1. Check my math. Easy to make a mistake, and we don't want to dig our hole for ourselves. Do you agree with what I did? If you catch a mistake, don't hesitate to speak up. Any questions? Are you following what we're doing? We're trying to figure out the a, b, and c so that alternate version of the integral we were given equals the original integral we were given. So we can easily do the antiderivative. Okay, so now we got 3 equations and 3 variables. Again, however you want to solve that system of equations, you're welcome to do. You can do elimination, you can do substitution, you can do matrix method. So what I noticed right away is I got a minus 4a and a 4a, although that will leave me an equation of b and c, which won't really help me there. So let's see. If I can eliminate c, what I want to do is, I see if I can eliminate c from the second and third equation, then I'll have a new equation of a and b, and I can combine it with equation 1, which is the equation of a and b. So I'm going to take my second equation here, and I'm going to multiply by 3, and I'm going to add them, add 2 and 3, and that'll make c go away. My new equation of a and b, then, I can combine with equation 1. So if I add these two now, I'm going to get, see if I can do it all here. So negative 12a and 4a, I think is negative 8a. Check my math. Negative 15b and 6b is negative 9b. That was 0. 0c equals, add them together, 1. Did I do it right? Check my math. So we got negative 12a and 4a is negative 8a. Negative 15b and 6b is negative 9b, and then 0 and 1 is 1. So now I'm going to combine that with my original equation, a plus b equals 1, and get, and so again, you can do it however you want. I can multiply this top one by 8, and that will eliminate a when I add them. That eliminates 8, so we get 8b minus 9b. 8b minus 9b looks like minus b equals 8 plus 1 is 9. So I think b is negative 9. And that's what I got before. Okay, and then that makes a, so if b is negative 9, that makes a positive 10. From this, a plus b equals 1. And then use either of these equations with c, like maybe this one would be the easiest right here, the red one, and you'll get c equals 5. Negative 40a plus 45b. Is it negative 5 or 5? It should be negative 5? Did I write it down wrong in my notes? Okay, let's see. So a is 10. Negative 40, negative 5. So we got the a, b, and c that make our original integral equal to this integral. And now we can solve that one. So it's, I'm just going to come up here and replace it. You could rewrite it if you want underneath what you've written. I'm going to come up and replace these. A is 10. B is negative 9. C is negative 5. That's what that original integral equals. Question? Okay, so integral of 10 over x minus 3. We should have that one down by now. 10 times natural log, absolute value, x minus 3. Same thing with negative 9 over x minus 2. Negative 9, absolute, or natural log, absolute value, x minus 2. How about negative 5 over x minus 2 squared? Another easy one, but no longer natural log. So it's a little undoing the chain problem. Let's just do that. So the negative 5 just comes along for the ride. And what do we got? We got x minus 2 to the negative 1. It's just power rule, right? But if we were to take the derivative of that, we would get positive 5x minus 2 to the minus 2. So then we need to take the opposite, right? Take the opposite of it. Get rid of the negative, and now the derivative of that is negative 5x minus 2 to the minus 2. So you've got the first two. So I'm writing the solution here. It's going to be the first thing plus the second one. We talked them through. Then plus 5 plus c. Questions on this example? If you're not sure about something, it's probably lots of people that are also not sure. Yes, please. We're doing the antiderivative. So we're doing antiderivative of that, right? So take the derivative of this. What do you get? Negative 5 x minus 2 to the negative 2. That's the one we got. You see it? Yeah, we're doing antiderivative. So it's basically power rule. We've got power negative 2. So antiderivative means power will be negative 1. Other questions? Okay, so let's look at another example. So, first question, is the degree of the numerator less than the degree of the denominator? Certainly. Degree of the numerator is 0. Degree of the denominator is 3. Can the denominator be factored? What can factor here? X. X times? Can it factor any more than that? Is that x plus 2 quantity squared? Is that x plus 2 quantity squared, that second term? should be sure to the answer to that question. It's a resounding what? No. There's a middle term. If you do x plus 2 quantity squared, you have a middle term for x that you don't have there. So this is done. We can't factor x squared plus 4 any further without complex numbers, okay? Without complex numbers. So we're done here in the real numbers. So now the question is, how does this look like in decomposed form? So it's going to be something over, or let's see. It's going to be over x and over x squared plus 4. So remember what we said. What you're going to put in the numerator is going to be an expression that's 1 degree less than the denominator. 1 degree less. So what's 1 degree less than x, or a linear term? Just a constant. What's 1 degree less than a quadratic? Power 1, right? 1 degree less than power 2 is power 1, or linear. So, but we need a full linear term. So bx plus c. So when you have a quadratic term in the denominator, that's not a linear term squared or cubed or the fourth. It's fully factored, and it's can't be decomposed any further than x squared. You're going to have a linear term, which is a full linear term, would be bx plus a constant. So remember in the last example, we had x minus 2 squared. That's not considered quadratic. The factor is x minus 2. So all you need is a constant up there. That's what we had in the last example. But this is not a linear term squared. It's a true quadratic that cannot be broken down anymore. So because it's a power 2, we need the linear term up there, 1 degree less. Okay, so we do it the same way. Here we go. I think you can finish it. See if you can finish it. Don't spin your wheels at the beginning. Get off to a good start so you can finish on time. Okay, if you haven't looked up yet, check your work. Check your work. Okay, and so how do we do this second antiderivative? Negative 5 halves x over x squared plus 4. Do you recognize what we have to do that? Notice that this is essentially x to the first is essentially the derivative of x squared. Therefore, undoing chain. So what will it be? Negative 5 halves, natural log, x squared plus 4. And then we'll need another 1/2 for the x squared. See how fast I did that? This is the goal, that you can do it this fast. Negative 5 halves times 1/2, natural log, x squared plus 4. Can you do it that fast? That's what we were after. That you can just now start writing down these answers to these undoing chain rule problems. That's just the second one. Okay, that's just the second one. Okay, now I want to add another WebWork set to the one that's already due Wednesday at 8:30. Listen carefully. With these WebWork homeworks, whenever you have WebWork due, we will often have a short quiz at the beginning of class, a written quiz, to keep you accountable to really learning that stuff in the WebWork. Okay? You have to not just get 100% of the WebWork. You have to learn those techniques that we're teaching in those sets. So whenever there's a WebWork due, just from here on out, rest of the semester, expect a short quiz on that stuff at the beginning of class, lecture. Okay? See you Wednesday.